Hello. So in this video, I wanted to talk about something known as the derivative. And I wanted specifically to talk about the derivative as the slope of a graph of a function. So um, I showed you in a previous video that we could get the slope of the graph of f of x equals x squared at any point on that graph, we'll say that has coordinates a comma a squared, by picking a second nearby point on that graph, a plus delta x comma a plus delta x the quantity squared, finding the slope of that secant line that passes through those 2 points, and then taking the limit of the slope of that secant line as delta x goes to 0. So in the graph below, I don't know if I did that. In the graph below, we have, so the red curve is the graph of x squared. The black line is the secant line that connects the 2 points a comma a squared and a plus delta x comma a plus delta x squared. And so I made the case in a previous video that if we take the slope of that secant line and find the limit of that as delta x goes to 0, that we would have the slope of the graph of x squared at the point a comma a squared. And let me review why that is logical, why that should work. If we take a look at these 2 points on the secant line, so the x coordinates are a and a plus delta x. In the limit as delta x goes to 0, well, let me say this first. The difference in those x coordinates is delta x. So in the limit as delta x goes to 0, effectively the difference in x coordinates would be nothing. And if you notice, so too would be the difference in the y coordinates. And in other words, that second point that's higher up on the graph would really be the same as the first point. So the secant line would no longer be a secant line. It actually would be the slope of a tangent line to that graph. So I'm going to see if I can sort of sketch that in. So there we go. So there would be that tangent line. And so, the slope of that tangent line should logically be the slope of the graph there. So by taking the limit of the slope of that secant line, we find the slope of that tangent line, which means we found the slope of the graph at a comma a squared. That was the reasoning we did in the last video. So I'm going to show you mathematically that reasoning again. So what we're doing is we're going to say that the slope of f of x equaling x squared at the point a comma a squared is the limit as delta x goes to 0 of the slope of that secant line, which would be the change in y coordinates, a plus delta x quantity squared minus a squared divided by the change in x coordinates, which would be a plus delta x minus a. We saw already the difference in those x coordinates is just delta x, and we can see mathematically that's true because those a's would cancel out in that denominator. And then to find that the limit of that fraction, we can first break down a plus delta x, the quantity squared. It's just a plus delta x times itself. So we could multiply that out. And when we do, let's see, so we would get a squared plus 2a delta x plus delta x quantity squared. So that would be that product. And then we still have minus a squared in that numerator. That's all over delta x. And in the numerator, we see that we have a squared minus a squared, so those cancel out. And then what we have remaining in that numerator has a common factor, delta x, so we could pull that factor out. So I will rewrite the fraction. So we're taking the limit as delta x goes to 0 of delta x times the quantity 2a plus delta x. And that's all over delta x, and we're trying to find that limit. We see now in the fraction, as long as delta x isn't exactly 0, we can cancel out those delta x's in both numerator and denominator, this one and that one, I should say. And then to evaluate that limit, all we have to do is really at this point, substitute 0 in for delta x, and so we get 2a. So that represents exactly, not an approximation, but exactly the slope of the graph of f of x equals x squared at any point a comma a squared. We made that case in a previous video, or I should say I made that case and we just saw that once again. Now, of course, when we talk about a comma a squared on the graph of f of x equals x squared, I mean, a is not any special value. It's just the x coordinate of a point on the graph. So since it's not special, we could just call a x. So what we really found then is a way to get the slope of the graph of f of x equals x squared for any point x comma x squared. And all we would have to do is replace a with x. So the slope of the graph of x squared for any point on the graph is really just 2x. So that's cool. That's all well and good. We found now that, of course, we can get the slope of a graph that's kind of curvy. We're not limited any longer to just finding slopes of lines. We can get the slope of a curvy graph, at least specifically the graph of x squared. But can we do better? Can we generalize this process? And if we can, what does that process look like? So let's see if we can reason this out. Okay, so below, I've taken the liberty using Desmos of drawing a graph of some generic function f of x. So that red graph is the graph of f of x, or I should say the function y equals f of x. And I've also drawn a tangent line to that graph at a point a comma f of a. So the green line we're seeing is that tangent line. And I've also indicated a second point on the graph of y equals f of x, that point having coordinates a comma, or sorry, a plus delta x comma f of a plus delta x. So we have 2 points on the graph of the function, and I've drawn a blue secant line connecting those points. And so just as we did with x squared, we could use the secant line to approximate the slope. And then in the limit of the slope as delta x goes to 0, that secant line would become the tangent line, and that approximation would no longer be an approximation. We would find exactly the same, we would find exactly the slope of that tangent line, as well as the slope of the graph at the point a comma f of a. And again, I'm going to just mark on our graph here that if we look at the horizontal distance between those 2 points, that's a plus delta x minus a, which is just delta x, which is why taking the limit as delta x goes to 0 would bring this second point closer and closer to that first point. And that's why we can say that that limit give us the slope of the graph. So anyway, let's follow that process here. So we could say the slope of the graph of this generic function y equals f of x at the point a comma f of a, it's really just the limit of the slope of the secant line as delta x goes to 0. So we're taking the limit as delta x goes to 0. And the slope is change in y over change in x. That would be f of a plus delta x minus f of a over the change in x, which would be a plus delta x minus a. And as we've already seen, that change in x values is really just delta x. And so the slope at the point a comma f of a would be the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Okay, and so we found that expression, which you can see printed out here. So there's that expression for the slope of the graph of some generic function at the point a comma f of a. And as we recognized previously, well, a comma f of a, that's generic as well. A is not any special value. It's just the x-coordinate of a point on that graph. So what we're really saying is that we have an expression for the slope of the graph of some generic function f of x, really at any point x comma f of x. And all we would have to do is replace a with x. And when we do that, we get this thing known as the derivative of f with respect to x, which is this. So there's the derivative. And again, what we see is the significance of that. There's actually other meanings to the derivative, but at least from a graphing standpoint, the significance of this thing that we're calling the derivative is that it represents, when that limit exists, you could say either the slope of the tangent line to some graph f of x or the slope of the graph of f of x at a particular point on that graph. Now, if you look in any calculus book, there are actually several different notations for the notion of this thing called the derivative, and I'll say the derivative of f with respect to x. One of the most popular notations is f prime of x, and this comes from Isaac Newton, who's credited for having founded really this thing that we call calculus. But another popular notation is this. It looks like a fraction, but it really reads df dx. And this notation comes from Gottfried Leibniz. He and Newton, they were contemporaries, but they were not colleagues. They were not homies. They did not work together. They worked separately, but they were both working on the same thing. So it's to try to find a framework for finding the slope of curvy thins. The reason Gottfried Leibniz notation looks like a fraction is because when you think about it, it's the limit of a slope. The slope is a fraction, so that's why Gottfried Leibniz notation looks like a fraction, but it's really not necessarily. Okay, now if you consider y equal to f of x, then a third popular notation, which you'll see in many calculus textbooks, is you'll see dy dx. So these are a few popular notations for the derivative of a function. But in any case, for whatever notation you use, the derivative is given by this, at least by definition, right? Okay, so here we go. So let us now evaluate some derivatives. And I'm first going to do something that is sort of stupid. I'm going to evaluate f prime for the function 2x minus 5. Okay, so let's do that. So if I do that, f prime, as we saw, is really the limit of the slope of a secant line. So f prime is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. That was the definition that we came up with earlier. We're going to apply this definition to the function. So it's the limit as delta x goes to 0. Now, f of x is 2x minus 5, so f of x plus delta x would be 2 times the quantity x plus delta x minus 5. So that's f of x plus delta x. If I put that extra paren there, I didn't need to do that. Let's see, say minus f of x, which is 2x minus 5, and I'm taking that over delta x, and I want to find the limit as delta x goes to 0. So again, just to remind us, this part here is really f of x plus delta x, and this part here, of course, is f of x. Okay, so, all right, so we would end up with, let's see, so it'd be the limit as delta x goes to 0 of, and when I distribute, I'll have 2x plus 2 times delta x minus 5, and then when I distribute in back here, it would be minus 2x plus 5, because a negative times a negative will be a positive, and that's all divided by delta x. And I want to take the limit of that fraction. I'll first simplify some stuff. I see that I have in the numerator 2x minus 2x, so those cancel. And I also see minus 5 plus 5, so those cancel. So now I'm taking the limit of the fraction 2 delta x over delta x. And one thing that I see as well is that I can cancel out those delta x's. So it looks like I found the derivative of 2x minus 5, that derivative being 2. Now I said that was sort of stupid. Why is that stupid? Well, the reason it's stupid is because we didn't have to do that. It's a linear function, y equals 2x minus 5. We talked about the derivative being slope, but this is just a line. The slope of the line is 2, so big whoop, we haven't really found anything we didn't already know. It just took us longer, but at the very least, we can see that this notion of derivative, hey, that seems to work. So let's now try it on something that's more novel for us. So here's another example. Okay, so this time I want to work with the function f of x equals square root of x, and I want to first find the derivative of that function. And then I want to evaluate the derivative when x equals 4 as well as when x equals 9. And then I want to look at those values and see, hey, does the derivative tell me anything about the slope of the graph of square root of x? Okay, so let's go through that process. Okay, so again, f prime, so I'm doing part A now. F prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Once again, I'm just writing the definition of the derivative, but I'm now going to apply it to the function. So it would be the limit as delta x goes to 0. F of x plus delta x would be really the square root of x plus delta x. And then minus f of x, which is simply f of x is the square root of x, and I'm dividing by delta x, and I want to take the limit of that ugly looking fraction. How the heck do we take that limit? Well, fortunately, there's a trick for that. What we can do is we can multiply both numerator and denominator by what I'm about to show you. I'll say square root of x plus delta x plus the square root of x, and I'll multiply the numerator and denominator by that. So I'm not changing the value of that fraction. I'm making it look a lot more complicated. But what we should see is, we'll see that in a minute, that we can actually evaluate that limit. Now, when we multiply those two fractions together, we're going to get, so I'm still taking the limit as delta x goes to 0. It's kind of like a FOIL type deal, right? We're going to FOIL those two numerators together. When we do, the first thing we would see, the f part of FOIL is the square root of x plus delta x times itself. The square roots would go away, and we'd end up with x plus delta x. Now, when we take the outer part of FOIL, we would get the square root of x plus delta x times the square root of x, and then minus really the same thing, the square root of x plus delta x times the square root of x. And then the last part of FOIL would be minus square root of x times positive square root of x. Again, the radicals would cancel out, so we'd end up with minus x. And then all of that would go over, and I'm not going to even multiply out those denominators. I'm going to leave the denominators as is. So it's delta x times that quantity, square root of x plus delta x plus square root of x. And I want to see if I can take that limit. Well, one thing that I see in the numerator, lots of stuff cancels out. I have x, and then I have minus x. And then I also have, let's see, the product of those two square roots, root x plus delta x root x. So those cancel out as well. And then finally, I see with what's left in the numerator, well, the only thing left in the numerator right now is delta x, which is a common factor with delta x in the denominator. So when I cancel those out, effectively I'm taking the limit. Let's see, let me write all this down. The limit as delta x goes to 0. When I cancel out those delta x that I crossed out in blue, well, my numerator would just be 1, and my denominator is that funny thing that I got in the bracket, x plus delta x, the square root of that, plus the square root of x. And this limit now is pretty easy to evaluate. All I'd have to do is really just let delta x be 0. So that's 0, which means in the denominator I have x plus delta x, which is just 2 of them. So the derivative, the expression for the derivative is just 1 over 2 square root of x. So we've done part A. We've evaluated the derivative of square root of x, and we get this expression 1 over the quantity 2 root x. So now in part B, we'll evaluate those derivatives when x is 4 and when x is 9. Okay, so f prime of 4, well, that would be 1 over 2 times the square root of 4. The square root of 4 being 2, so that's 1 over 2 times 2, or 1/4, right? And f prime of 9, very similar. We would have 1 over 2 times the square root of 9. The square root of 9 is 3, so we would have 1 over 2 times 3, or 1/6. So one thing that we see then, because that's part of the question, what these values tell us, one thing that we see is that as x gets bigger, like when x goes from 4 to 9, it looks like the derivative and therefore the slope gets smaller. It goes from 1/4 to 1/6. Yeah, so there you go. And as a closing thought here, okay, so below, again, courtesy of Desmos, we have a graph of square root of x. And we evaluated f prime of 4 and f prime of 9. In other words, we evaluated the slope at those points, 4, 2, and 9, 3. And sure enough, as we predicted, the slope gets less and less because we see that the graph sort of tapers off. It's becoming more and more horizontal looking. One thing that you might also notice from the graph is that regardless of where we look, that slope should always be positive. And that's something else that the derivative tells us, right? The derivative expression was this thing. Square root is always going to be positive, which means that that slope should be positive for all values of x on the domain. So the derivative predicts that for us. And again, we can see that from the graph. So there we go. So there is the derivative, in summary, as the slope of the graph of some function. Thanks for watching. By the way, I forgot to introduce myself. This is me, the Math King. I hope you like this, and if you do, I hope you will click like. Thanks.